Hello everyone. Welcome to this video presentation of our NeurIPS DLDE workshop paper entitled Bridging the Gap Between Coulomb GAN and Gradient-regularized WGAN. My name is Siddharth Ashokan and I am a PhD student at the Robert Bosch Center for Cyberphysical Systems at the Indian Institute of Science, Bangalore. My co-author is Professor Chandrasekhar Selamantula from the Department of Electrical Engineering, also at the Indian Institute of Science. Before we begin with the specifics of the paper, let's start with a brief introduction to Generative Adversarial Networks, or GANs, a framework that's gained a lot of popularity over the past decade for their ability to generate high-resolution photorealistic images. Delving a bit deeper into this formulation, GANs are an unsupervised min-max training framework for learning a given data distribution, typically images or speech. As an example, we consider images here, sampled from the Met Faces dataset. These samples can be seen as coming from an underlying distribution, PD. The generator network is like an art forger. It accepts noise as input, usually drawn from a Gaussian or uniform distribution, and learns to transform it into realistic target samples following an output distribution PG. The discriminator network, akin to an art critic, is typically a two-class classifier network. Its task is to differentiate between the real and fake samples and percolate that information back to the generator through appropriately defined loss functions. The generator is trained to minimize this loss, thereby creating samples that are continually harder to classify by the discriminator. The objective is to learn the optimal generator, one that creates samples that are indistinguishable from the reals, ultimately confusing the discriminator. Let's focus a bit on the losses used to train GANs. Broadly, they are of two kinds. The first is that of divergence minimization. The original or vanilla GAN formulation by Goodfellow et al. And subsequent variants such as the least squares GAN or FGAN fall under this category. For example, the vanilla GAN considers a cross-entropy loss, and the generator can be seen as minimizing the Jensen-Shannon divergence between the data and generator distributions. The LS GAN solves a least squares interpolation problem with the generator minimizing the Pearson chi-square divergence. In general, any F divergence can be considered, giving rise to the entire family of F GANs. However, in general, it has been shown that divergence minimizing GANs are unstable to train. Vanishing gradient issues occur when the supports of the target and generator distributions are non-overlapping. In order to overcome this limitation, integral probability metric or IPM GANs were introduced, wherein the discriminator approximates a chosen distance metric, and that choice of IPM results in a corresponding constraint class for the discriminator function. Various popular GAN variants such as the Wasserstein, Sobolev, and Fisher GANs fall within this category. For example, the Wasserstein or WGAN minimizes the Earth mover's distance between the real and fake distributions, with the Lipschitz 1 constraint on the discriminator. Similarly, the Sobolev GAN draws from functions from Sobolev faces, hence the name, with the GAN loss enforcing constraints on the norm of the gradient of the discriminator. In practice, however, the Lipschitz constraint is challenging to implement, and a plethora of variants such as WGAN GP, WGAN LP, WGAN ALP, etc. all enforce some form of the gradient penalty to approximate the Lipschitz constraint. While divergence minimizing and IPM GANs are able to explain most GAN formulations, some variants, such as the GAN with relativistic discriminator or Coulomb GANs, don't really fall within these two categories. Our paper focuses on analyzing one such GAN variant, which is the aforementioned Coulomb GAN. Within this framework, a charge potential interpretation is given to the real and fake samples. Essentially, the data samples can be seen as negative charges and generator outputs as positive charges. The generator is trained to minimize the potential field induced by these charges. The images on screen give us a feel for the Coulomb GAN loss landscape, with the potential field induced by the reals and fakes being reminiscent of those observed in electrostatics. In Coulomb GANs, the generator is trained to minimize the potential field phi, which involves the Plummer kernel kappa. The Coulomb kernel is a singular version of the Plummer kernel with epsilon equal to 0, making its implementation relatively unstable. In practice, a discriminator network is still used and is trained to approximate a sample estimate of the potential phi hat in the least square sense. We'll be coming back to this sample form of the Coulomb GAN potential within our proposed formulation as well. The core question we seek to answer in this paper is whether there exists a link between the IPM GAN formulations and the potential minimization in Coulomb GANs. The answer is indeed a yes, and in particular, we show that Coulomb GANs are a special case of gradient-regularized Wasserstein GANs. We analyze the regularized Wasserstein GAN cost, leveraging results from the calculus of variations, and show that the optimal discriminator solves a Poisson PDE, whose Green's function is precisely the Coulomb kernel. We implement the optimal discriminator in GAN learning through a radial basis function or RBF network, and present preliminary results on learning 2D Gaussian and Gaussian mixture data comparing against baseline WGAN and Coulomb GAN variants. To motivate the proposed formulation, consider the Coulomb GAN potential parameterized by n, the dimensionality of the data. As noted in literature, the potential is a generalization to the classical results developed in electrostatics in 3D and is the Green's function to the Laplace operator. To recall, this implies that applying the Laplace operator onto the Coulomb potential gives us the direct delta function up to some constant c. While not too important within the GAN formulation, the constant is a combinatorial term involving gamma functions and the surface area of a unit sphere in Rn-1. Further, we also observe that the Coulomb kernel appears in mesh-free interpolation when considering gradient-based regularization. In the present context, we therefore consider applying the gradient constraint over the union of supports of PD and PG, and in the case when they are non-overlapping, the convex hull formed by those supports. We consider the Wasserstein IPM GAN cost with such a penalty term on the gradient energy of the discriminator. To derive the closed form discriminator within this framework, we consider optimizing the cost through the calculus of variations. Specifically, expanding the expectations in LD, we obtain an integral cost whose optimum satisfies the Euler-Lagrange conditions. Such an optimization of the proposed cost yields a partial differential equation that the optimal discriminator must satisfy, which is in fact a Poisson PDE. The link to the Coulomb GANs are getting clearer now. Convolving both sides of the PDE with the Green's function gives us the optimal discriminator in closed form up to a scaling constant. To cement the links to Coulomb GAN, we consider this optimal discriminator, simplifying by expanding the convolution terms and replacing the integrals with their sample estimates yields the exact family of Coulomb GAN potential functions. Including a correction term to eliminate the singularities would yield the family of Plummer kernels as well. Another interesting insight is that the proposed formulation is merely the particular solution to the discriminator PDE. In fact, we can now derive the general solution also incorporating the homogeneous component, which are first-order polynomials. However, the actual choice of the coefficients would depend on the boundary conditions enforced on the discriminator. While we defer a more detailed analysis of choosing the homogeneous component to an extended version, for experimental purposes in this paper, we set P to be 0 so that the solution matches the Coulomb GAN formulation exactly. Now that we have shown that the Coulomb GAN discriminator is the optimal solution to a gradient-regularized WGAN optimization, we consider the task of implementing this optimal discriminator. For comparison, amongst the baselines, most WGAN variants enforce a gradient penalty empirically, evaluated over interpolation points of the real and fake samples. This allows for efficient implementation through backpropagation. Coulomb GANs, on the other hand, consider the sample estimate of the potential and train the discriminator to approximate it in the least square sense. The least squares formulation is chosen as it allows efficient computation of the kernel. We also consider the closed form sample estimate dp star. However, we implement the solution as an RBF network with predetermined weights. As a result, the training of the generator remains adversarial, which has been shown to improve generated sample quality, and the generator still has access to dp star, albeit a sample approximation of it. We show that this is superior to the least squares approximation obtained in Coulomb GANs. Given the RBF approach, we name our method RBFCoulombGAN. GAN. The current slide depicts the proposed GAN framework. Note that the discriminator is an approximation of the optimum and therefore does not require gradients for training. Only the generator is trained. As part of the workshop paper, we perform preliminary experiments on learning 2D Gaussian data. The plots depict the generated and target data samples as iterations progress, when the target is red and the generated data is green. The contours depict the level sets of the discriminator. At the initial iterations, it is clear that implementing the closed form RBF is superior to both Coulomb and Wasserstein GAN approaches. Although Coulomb GANs are superior to WGANs, the least squares discriminator is unable to learn the optimum one shot, unlike in the proposed RBF approach. Similar performance gains were observed in Gaussian mixture learning tasks as well, where RBFCoulombGAN is able to learn the exact location of the modes in the target data, accelerating convergence. Comparing the models in terms of the Wasserstein 2 distance between the generator and data distributions corroborate these observations quantitatively, where RBFCoulombGAN converges faster and to a better or lower value of the metric. To summarize, in our paper, we derived the functional optimum in gradient-regularized WGANs and showed that the optimal discriminator solves a Poisson's PDE, whose solution coincides with the Coulomb GAN formulation. Implementing the closed-form discriminator via an RBF network results in superior performance compared to the baselines on synthetic Gaussian learning tasks. For additional insights, please check out our paper and poster. The source code is available at our GitHub repo, which can be accessed by scanning the QR code above. As part of our future scope, we will explore higher order generalizations of the Plummer kernel, as well as consider extensions of RBF-Coulomb GAN in generating images. One could also consider analyzing other GAN costs that don't conform to divergence or IPM minimization, derive similar PDEs that govern the optimum, and design network architectures inspired by them. These are the key references cited across the talk. And with that, I'd like to thank you all for your attention, conclude my talk, and open the floor to questions and discussions.